You might be one of those kids who sits in the back of math class thinking to yourself, when will I ever need to know this outside of school? Well, let's go back to 1943. It's World War II and the Air Force is launching an attack on Germany by bombing dams. Lancasters are to fly over the water and drop skipping bombs, specifically designed to avoid the existing defenses around the dam and cause flooding. The bombs can't be dropped anywhere though. There are multiple factors that affect the bounces of the bomb and therefore the path they take to reach, or not reach, the dam. We need a way for the pilots to tell when to drop the bomb correctly. Here's where the math comes in. Let's start from the basics. How high up should the plane be when the bomb is released? Well, we've done some tests and know how high we should be, but it's too close to the water for the conventional measuring devices on the plane to be accurate. Instead, we have fixed lights to the bottom of the plane. They are placed a known distance apart on the plane and are angled in towards each other. The pilot knows he has to release the bomb when the beams from these two lights hit the water in the same spot so that it forms a triangle. But how exactly does this work? Well, since it's a triangle, we do know a few things. All the angles add up to 180 degrees. So with some simple subtraction, we can find out the angle of the triangle at the water. We now know an angle and the length of the side across from it. That means we can use sine law to find the length of one of the sides of the triangle. This is enough information for the height of the triangle to be calculated using the b sine a rule. Once we know the height of this triangle, we know what angle from the plane the lights are pointed at, so we can use the sine law to find out how far from the water the top of the angled triangle is. That's how we know that if we make a triangle with the lights, we can guarantee that the plane is the right height off the ground.
Next up on the list of important things the pilot needs to know: how far away the plane needs to be from the dam when the bomb is dropped. This time we'll have another device to help with the process. We'll call it a triangulator, and it looks like this. The pilot holds it up to his eye and looks through. When the pegs on the ends of the triangulator's arms are in line with the sides of the dam, that means the plane is the correct distance away. To understand this better, let's take a look at the top view. When the dam is in line, it makes a triangle from the sides of the dam to the pilot's eye that goes through the two pegs. You can make another triangle around the pegs and to the pilot's eye, and this triangle is similar to the big one. That is to say, the proportions are the same. We can find out how much larger the big triangle is by dividing the length of a side of the big triangle by the length of the corresponding side in the small triangle. This means that if we know the height of the small triangle, we can multiply that by the scale factor, and we know the height of the larger triangle, and therefore our distance from the dam.
We should now take the time to consider the fact that the Germans aren't defenseless. They have anti-aircraft defense set up to try to shoot down our planes. But is it possible for them to take down the plane before it gets a chance to drop a bomb? To figure this out, we need to know the flight path of the plane. Once we have that, we also need to know the path that the anti-aircraft defense fires in. We then need to figure out where these two parabolas intersect. If one of the points of intersection is farther away from the dam than the distance at which the bomb is going to be dropped at, then there's a chance that the plane could be shot down before it gets a chance to drop. It's still unlikely, because the shot would have to be fired at the right time to ensure that the plane is in the point of intersection when the shot crosses the path. But it's still possible, so the pilot needs to watch out.
The Germans also have torpedo nets set up, and we have to make sure that the bomb we drop skips over those. But before we can figure that out, we have to analyze the way the bomb bounces. We've done some testing before heading out on the mission, so we have some information about the height of the bomb over time as it bounces. Let's take a look at just the peak heights of each bounce. We can figure out an approximate decay rate between the bounce heights by dividing each of the previous height and then taking the average of those. We can also get the acceleration of the bomb by finding the average of the second differences of the points in a bounce. This should come out to something around 9.8 because that's the gravitational field intensity on the surface of the Earth, and the rate should stay about the same for each bounce. We now have enough info to make a parabola for any bounce after the bomb is dropped. In vertex form, you can fill in h and k using the coordinates of the point the bomb is dropped from. If you remember physics class, d equals 1/2 acceleration times time squared. So dividing the acceleration we found by 2 will give you a, which you can then use to complete the equation for the first bounce. To find the next bounce, simply move the parabola down according to the bounce decay rate we found, and then shift it to the right so that the parabolas are touching on the x-axis. After we do this a few times, we have a good model of the bounce of the bomb, which allows us to easily check if the bomb touches the torpedo nets. If it doesn't come close, then we are good to go. So let's talk about the bomb itself. Not because it affects our calculations, but because a lot of thought was put into making this thing work. Now, how does this bomb, called the upkeep bomb, manage to bounce? It also has a lot to do with the fact that it has a backspin when it falls. The height of a point on the bomb over time makes a sinusoidal wave, which looks like this. Add in the fact that the bomb is falling, and it looks, wait for it, like this. We now have enough information to try it in real life. We did our own small-scale test run, which was a success. It turns out, in real life too, the mission was a success. So, eager math student, without this information, would we have been able to do this mission? No, I thought so. That leaves the score at Math 1, World 0.